Hi friends, today we are going to learn about photovoltaic inverter structures. Coming to the introduction, the PV inverter is the key element of grid connected photovoltaic power systems. Okay, and the main function of these type of PV converters is uh, that when the PV panels give the DC output, it had the output of the PV panels is taken by these inverters, and then it has to convert that DC power into the AC power, such that the generated AC power is grid synchronized. Okay, so depending on the PV power plant configuration, the PV inverters can be categorized as follows, like module integrated inverters, string inverters, multi-string inverters, mini central inverters, and central inverters. So coming to the first one, the module integrated inverters typically they have the ratings of 50 to 400 watts uh, for very small. Generally, they are used for very small PV plants. And coming to the second one, string inverters. String inverters generally have the ratings ranging from zero point 0.4 to 2 kilowatts, and these are used for the small rooftop plants with panels connected in one string. Okay, that's the reason they are called as string inverters. And coming to the next one, that's multi-string inverters. Multi-string inverters have the ratings ranging from 1.5 to 6 kilowatt, much better than the string inverters one. And this type of multi-string inverters generally are used for the purpose of medium to large rooftop plants with panels configured in 1 to 2 strings. So it has multi strings, 1 to 2 strings. That's the reason that they are called as multi-string inverters. And coming to the next type of inverters is mini central inverters. Mini central inverters have the ratings more than the 6 kilowatts. They have more than the 6 kilowatts of rating with three-phase topology and modular design for larger, and so these are used for the larger rooftops and small power plants in the range of 100 kilowatts, and typically they have the unit sizes of 6, 8, and 10, giving the like up to 15 kilowatts of rating. uh, Generally, the point to emphasize here is that the moment I have been telling you that the rating of 6 to more than 6 kilowatt and 1.5 to 6 kilowatt and all these ratings means that it can generate the output power of this much, for this in this range. So that's what I've been trying to tell you. So coming to the next point, yeah, actually this is the generally we have two types of mm, you know families based on which the PV inverters are derived. First one is H bridge topology, and the second one is neutral point clamped topology. So let's learn first of all, let's learn about the H bridge topologies. The inverters based on the H bridge topology are like uh, there are numerous H-bridge topology based inverters like Herrick inverter, H5 inverter, H6 inverter, H7 inverter, and H8 inverter. Generally, Herrick is used for a single phase purpose, and from H5 onwards, we can use these inverters for three phase purposes. So, so this is the basic diagram for the H-bridge family. Basic full bridge inverter. So you might have seen, in general, generally the inverter is based when you learn about the inverters in any field, like any applications, the general basic structure for the inverter will be like this only. So we have three switches: S1, S4, S3, and S2. This is called as basic full bridge inverter. This is the PV array and the filter CPV. Okay, and this is the grid. We have two inductors acting as the filters, L1 and L2. They yeah, connected to the line and neutral. Yeah, coming to the next slide. Yeah, the above circuit can be operated by using the three different modulation strategies, bipolar modulation, unipolar modulation, and hybrid modulation. So these three are the different modulation techniques that we are going to use for our purpose. So let's see about the bipolar modulation. In bipolar modulation, what happens is, when you give when the photovoltaic panel or PV panel gives the output, then the output mm, then the current flows like this. Okay, the current flows like this. So we in bipolar modulation, what happens is, uh, uh, the, we will be having the S1 and S4 and S3 and S2 synchronously turning on. Okay, synchronously S1 and S4 will turn on, and for the other switching state, S3 and S2 synchronously will turn on. So this process will go on repeating. So we'll be getting uh, waveform, an AC waveform, output waveform. Okay, so let's see how the operation goes on. So when the current flows from here, then we have a closed path here, then it tries to flow from here, then it goes here, we have the filters, and it flows from here to here, and again we have a closed path here. Since this switch is closed, it's flowing from here, otherwise it might have been stopped there. So stopped, or it might have been flowing like this in this closed path itself. So because of a closed up and a path available to go from there, it's flowing like this. So it's flowing here with the negative point. Okay, and this one is grounded here. So we have S1, S4 or S3 and S2 are closed. So these are complementary switches operating at a high frequency. So this is for the positive output current. Okay, so what happens when the negative output current is provided? uh, yeah uh, let's ignore that one for a while. Let's see for the other complementary switch operation. When the current flows like this, uh, here we have a open, consider it's open like this, the same one it's been shown here, that's here. Okay, assume that is here, so it will not flow from here, then it goes here, and we have a assume that this switch is closed, then it will flow from here, flow to this flow from this switch, and it will come down and down, and it will go to this path, and it will flow like this, and it will come here, and then it will come down, and this switch will be closed. Since complementary switch to S1 and S4 is S3 and S2, so S3 and S2 both are closed, and S1 and S4 are open switches. So the current cannot flow from S1 and S4, and the current is flowing from S3 and S2. So when the current flows from S3 and so at this point the current flows from this S2 and reaches to the negative point. So the loop has been completed. So this is the way in bipolar modulation the current flows. And coming to the next point, we have sorry in the same way, when we consider for the unipolar modulation, we will be having S1 and S3 turned on, and S2 and S4 turned on complementarily. Similarly, like we have been uh, turning on S1 and S4 and S3 and S2 complementarily. So in the same way, we are turning on S1 and S3 and S2 and S4 complementarily. So let's see what happens when S1 and S3 are uh, turned on. Let's see when the current flows from here to this point, and this switch is closed, so it will go from there to the next switch. Then comes down like this switch is also closed. Actually, what happens is when the current flows from here to here, then this switch, this diode is actually turned on. Okay, it will go from this diode. This switch is okay. This and the S3 is also closed, and D3 is also closed. I mean that's turned on, and S1 is closed. Okay, so then it will flow here, and it will come down from here to here this point, and it will come back to this. Okay, the loop is completed. And what happens when S2 and S4 are closed? At that point, when the current flows from this point to this point, it will flow here, and it will come to this point, and it will go back to that. So the loop is completed. So that's it for today. Thank you. Thanks a lot. Please subscribe for the channel if you want to learn more from this channel. Thank you. Thanks a lot.